Live streaming is on.
Can see?
Yes, can see. Yes.
Yeah.
Yes.
Start. Let me restart first. All right, so basically this, can hear my voice, right? So basically this project is Parkinson prediction. And why this project come out is because Parkinson's patients, right? They are all very immobility convenience, which means that when they want to move from one location to another location, it's very hard for them. And for them to go to a clinic to examine their Parkinson's health, and it is very difficult to have a routine checking. So this project allows them to stay at home and have this algorithm will predict their Parkinson's health. So let me load the data first, and then this is the data collected. So given the problems of the patient's immobility, so that's why this project set off. So the patients no need to go to the clinic, but using a tele-monitoring device that can collect their voice and can predict how severe the patient's Parkinson disease is. So this is the data which has 5,000 observations and 22 variables. And so for demographic data, it has a subject, age, and the gender. And so for this here are all voice measures. For example, the jitter is when the patient speak to the microphone that installed at their house. So all these attributes will collect what is the voice attributes are collected. And for the target is total UPDRS. The higher the total UPDRS, then it will indicate that this patient is more severe. All right. So as we can see from these attributes, some of the attributes data type is not correctly labeled. For example, the sex here is integer, but actually this is categorical. And the other one is subject. Subject is categorical also, but it's labeled integer. So the next thing is we need to change the data type into the correct one. So for the sex is the categorical, subject is also categorical. So as now we can see is already changed to factor and factor. Then we move on to explore the data by using the summary data. So from this result, we can see some problems here. For example, the test time, we got a negative value. For test time cannot be negative value, is only for positive. And the other one is we also observe the motor UPDRS has many NAs, which means non-available data missing value, 663. The other thing is also missing values for NHR, which is also the voice measures attributes, which have 399. So in order to solve this issue, then we also can calculate how severe is the missing values in this data set. For example, the 663 is come from this one, motor UPDRS, and then we divide it by total observations, and then it has 11% of missing values. Same goes to the NHR, which has 399 missing values, and it has near to 6.8%. Then because because the motor UPDRS actually is sharing quite similar information with the total UPDRS. If don't have this attribute, actually we can take this attribute as our dependent variable. So because it has 663, then we decided to drop it, and then we use only the total UPDRS as the dependent variable. So now we drop the motor UPDRS, and then we examine again the distribution of the attribute NHR. NHR, to recall it, is this one. It has a quite high number of missing values. So from this histogram, we can see it has a right skew distribution, very right skew. And this is also one of the problems that we need to normalize it and then make it into center. Then we decide to retain the NHR because it's not a very big value. And because it has right skew, so we decided to impute the missing values as median. Why median why not using the mean value to impute? Is because it has a right skew. So if we use mean to impute the data set, then some of the values might not appropriate. So median is more appropriate to use because it has right skew distribution. Then we examine it again, the summary. So now the test time haven't fixed yet. It still has negative value, but the non-available values is already fixed. Non-available values already fixed for the NHR. NHR now already imputed with medians, and the motor UPDRS already dropped. So there are no missing values already.
Maurice,
Yes.
what is the NHR? Stand for what?
Okay, so it stands for a type of voice measures collected. So for the jitter, shimmer, NHR, RPD, DFA is very specific. It's like a vibration. It's like a voice vibration. So it stands for a specific vibration for the voice collected in order to examine the Parkinson's disease. So if any question, you can just disturb me and then I'll try to answer. And next, I will use the box plot to identify the outliers. So as we can see, age is not a big issue. Test time is also not a big issue. But the dependent variable here, total UPDRS, to recall it, it stands for the severity of the Parkinson disease. And jitter is a big issue. So it has many outliers above the upper boundary. And jitter absolute is also has a very high problem here. Same with jitter IIP. And almost all voice measures also have outliers problem. So visualize from the box plot. Almost all, except DFA doesn't have the outliers problem. So the next step is we need to use interquartile rule to remove the outliers. Actually, it's not remove, it's replace the outlier by the upper and lower boundary. So, okay, this kernel here is a bit funny because me and our team write a long one. Actually, it can replace by a for loop here, but because we try again using a for loop, but it come out with error, so we decided to just explicitly write everything down here. So this kernel is just to replace all the lower and upper boundary, to replace all the outliers with lower or upper boundary by using the interquartile rules. So let me run the cell here. So after running the cell, all the outliers are replaced. And also remove the instances with negative test time because time cannot be negative in our project. So let us check again the dimension. So it has 4,437 observations with 21 attributes. So continue. So now is to separate the target and features. Our target is the total UPDRS and the features. So the reason why we need to separate the target and features here is because we want to transform the data set by normalizing it. Because our target UPDRS, we want to keep it as the original values, no need to normalize it, so we keep it away first. Okay, so now let's check with the transformation method. Because just now I have mentioned the data set have right skew problem, so we propose some methods, 4 methods here, to see which method can solve the right skew the most effective. Like for example, the original, square root, natural log, and log base 10. So for each attribute actually got visualized. This is original without solving the right skew problem. And then this one is solving using square root jitter. As we can see, it already become normalized. And this is natural log jitter. This is not that effective compared to square root jitter and log base 10 jitter. So we actually see it one by one, which one is the best to solve the right skew problem. And we found out that square root jitter actually is performed quite well. So we decided to use the square root jitter for our data sets. And natural log jitter and natural log and log base 10 actually doesn't really normalize it. It still has a bit left skew or right skew issue. All right, so this is all the visualizations. So we use the square root feature to solve the rescue problem. And then after solving the rescue problem, then we normalize the features into range of 0 and 1. All right, so we check again for the features. Is it already normalized? So as we can see here, okay, so the test time minimum is 0, maximum is 1. So all the features are also same. Okay, H is 0, maximum is 1. Subject is not affected because it's categorical values. And jitter also same, minimum 0, maximum 1. All the features are same, except the target, because the target we keep it away first. So from this summary, we know that our data already normalized, and now we can further examine the targets. So the target is not normalized, so the maximum is not 1. It's still retained as the original values. Minimum is not 0. So then we further explore our data set by checking the features range, mean, standard deviation, median, and and the IQR for the numerical features. So for the age, range is 49, and then mean is 64 years old. Standard deviation is 9, median at 65, IQR is 14. So we can see here the average participant age for taking this the testing of Parkinson's is 64 years old. And I forget to tell you that this data set only involved 40 participants in this project. But why become 5,000 observations is because they record their observations almost every day or within a certain time interval. So that's why it accumulates it into 5,000 plus observations. All right, so similar thing, we also generate the range, median, standard deviation, and median IQR for the rest of the features. So now we check again the distribution of the numerical features after transformation. So we can see now the features are already normalized. No more rescue problem by using the square roots. And then check the frequency of each category for categorical features. So our categorical features is the most useful one is sex. And for the subject, it's not that useful because it's just like indexing which number represent which participant. So it is not that useful for predicting the Parkinson's disease. So later on, we will drop that attributes. So we further visualize the gender in a pie chart. So male has 68% and female has 32%. Right, so just now we already checked the range, mean, standard deviation, median for features, but target haven't checked yet. So now we check for the target, which is the UPDRS. All right, this is the values, range 47.9, mean 28.7, and so on. And check the distribution of target. It's quite normal, so it's a good thing. And then we check the correlation of numerical attributes after transformation. So from here, actually, we can notice some problems here. Because, okay, so we have 20 plus attributes. And actually the jitter, absolute jitter, IP, jitter, PPQ5, all the attributes with the similar words at the beginning actually share very similar information. So which means that, for example, jitter relation with jitter ABS, it has a 0.86. And then for this jitter to jitter IP, it has 0.92, which means that it has very similar information towards this. So later on, we will decide to take only one jitter out of the jitter family. Similar to shimmer, if we see the shimmer correlations, then we can see that shimmer correlate with shimmer DB, it has 0.98, which is very high correlations. It's abnormal because we can deduce it share very similar information together. So to drop the attributes is because we want to reduce the dimensions of the dataset to make it less complex, and perhaps it can increase the accuracy. So if you guys want to stop me, then you can stop me, and then I will explain particular things. And for jitter, shimmer are same, and for the jitter, shimmer, actually for the jitter family, which has 1, 2, 3, 4, 5 attributes of family, actually we can only take one. Shimmer also same, shimmer 1, 2, 3, 4, 5. We also can choose one only as our attributes. So this is the findings we get from examining the correlation matrix here. And then we further examine the relationship between numerical features and target after transformation. So our target is total UPDRS and age. All right, so this is the linear plotting, which means it's a straight line plotting. And actually, obviously, we can see that the plot is not surrounding the line, which means that the straight line actually is not cover well all the plots. Same for the total UPDRS versus jitter absolute. All the points are actually scattered around. It's not the predicted line is not cover all the plots here. So same for all the other attributes for straight line. So then we examine the relationship between numerical features and target using nonlinear functions. So if we use the nonlinear trend line, then it actually can fit better than the linear line of plotting. Although it doesn't really cover all the points, but from this graph actually can tell us that it has non-linear relationship between the target and the features. So these are all the plots here. Right, so we move on. And then we can examine the categorical features with the target. Just now we already know the numerical features with the target, but we still don't know how is the categorical features perform with the target. So we examine it using ANOVA test. As we can see, the p-value here is very small, very small, 2e power minus 16. So which means that it has a significant relationship with the target. So it means that the gender here we can use as a predictor. Move on, we can determine the relationship of categorical features with targets. So, and then we use the selected features for modeling. So from here, right, we actually already know which features we want to choose. Which means that because we go to see the correlations matrix here, because we already know we want to choose only one attribute out of the family, which means one attribute out of the jitter family here. And then which attribute we want to choose? Actually, we choose the attribute that has the highest correlations with our targets. So the attribute we want to choose. So therefore we already know which attribute we want to choose. Then this is our selected attribute, which represent by an index number. And then this is so the jitter we choose already, and then shimmer APQ11. These two actually has a higher correlations toward our target. That's why we choose it. And then NHR and all the rest of the 5 still keep it as our predictors. And the subject already dropped, so it's already remained with age, sex, and the rest of the voice measures. So aside from the age and sex are our demographic predictors, and then the rest of it actually represent voice measures, the values of voice measures collected by tele-monitoring method. Then we check again the summary of the feature selected. So we double confirm it is the data that already pre-processed, which means that minimum is 0, maximum is 1, and then there are no NAs here, no missing values. And the head of the target, summary of the target. Summary of the target is still the same as before. Then we combine it again, our features and target. Again, why we need to combine the features and target is because we need to split the data into training set and testing sets. So as you can see, the total UPDRS already merged with the features. So now we can do the partitioning. We set the training set as 80%. And then for the cross validation, for the trend control is using cross validations. And the number of partitioning is 4, which means that each batch of cross validation, it has 25% of the data. 100 divided by 4. Correct. So now our data already split. 80% is training data and 20% is testing data. And we're using cross validation to check the R square, because this is regression problem. So we use R square to examine the how good is the data, how good is the modeling. So the next part is modeling. Okay, so now pre-processing already done. Now is modeling. For modeling, actually we got produced 4 types of model here, from linear regression, SVM, decision tree regression, and random forest regression. But I will only cover two modeling. One is linear regression. The other one is random forest regression. Okay, so just now we already explored the data. We know that this problem is a non-linear regression, but we also want to double confirm that is it really that linear regression cannot perform well. So we run one more time again the linear regression to double confirm that is it true. So we set the seed. This is random seed 1, 2, 3, and then 1M is represent the linear regression. To recall, the trend dot control is cross validation at 4, which means that it partition 4 times. To better visualize the trend control, I got another tab for you. Let me switch to this. And see, right? This one. This presentation here.
Yes.
Okay. So this is our overall data, which has 5,000 plus observations. And then 80% is for training data and 20% testing. So for the training data, we actually use cross-validation at 4-fold cross-validation, which means that for the training data, we split it 4 folds. Each fold consists of 887 observations. So for, let's say, for example, I take random forest regression. So actually, for each fold, the data actually will be trained by the random forest regression and output R square. And all 4 outputs of the R square will be summarize it by taking the average value. So why take the cross validation? It is because to know it can generalize well or not for the future data sets. Right, so I move on to my programming. All right, so this is the trend dot control I discussed just now, and then the metric here used is R square. So let me check the linear regression. So as expected, the R square is not performing well. It's only 0.17. And then the May here is very high, 8, and RMSE also very high. Then we build the linear regression and check the summary. Right. Okay, so then we again check the training and testing set errors. All right, so the training set RMSE is 9.8, which stands for the root mean square error. The R square is 0.18 for training set, which is very low. RMSE for testing set is 10. Although it is higher than the training set, but it is not this is not satisfying because the linear regression is just like a straight line and then it's not fitting well all the data. So the problem here is underfitting, which double confirm that this problem is nonlinear regression problem that we need to use nonlinear models to handle it. For example, the random forest regression is a nonlinear models that we can use to test it. So we see the residual plot for the linear regression. So as we can see, the residual plot is also not performing well because the data is not clustered toward the center of the graph. And if we split it half, and then it's not symmetric. So the residual, when the data increases, then the residual also going up. And yeah, so for the residual, if it want to perform well, the first thing is we need to see that all the data points are clustered toward the center, which means that is zero residuals. Then it's a good models. But for the linear regression, it is distributed like everywhere. So it is not a good model, and then the residual plot telling us that. So moving on, let me show you the random forest. So this is starting for the random forest modeling, and then set seed. Every seed we also set the same, which is 1, 2, 3. This is the random numbers, which means that we set for the random, which allows the result to come up the same every time we run it. And then the method is RF, which stands for random forest. Trend control is still the same. Cross validation at 4 folds. Metric R square. Tune length 10. The tune length here is telling us that the algorithm will try different values for the main parameter. Then let me print the FR. It will take quite some time. So actually, I already got a complete notebook that already run everything. Because just now I tried to run the random forest, it almost take me like 10 to 20 minutes. So the random, okay, so let me explain what is random forest here. Random forest is just like a decision tree, but it is a bunch of decision tree combined together to output a result. This is using the bagging method. Because decision tree actually has because decision tree is a nonlinear models that has high variance issue, which means overfitting the data points, meaning that it cannot generalize well to unseen data. If we use random forest, we combine different decision trees together, then it actually can solve the high variance issue for the decision tree. So normally it has better performance than the decision tree. But the downside for the random forest is it is very expensive to train, which means that it requires a longer time to train it. All right, so we can see the results. This is the parameters tuning. M3 is the hyperparameter for random forest, and we can see the which excuse me, which hyperparameter actually has the higher R square. So actually we can see is M3 equal to 8. It has 0.8933423 and one of the lowest of MAE. So we can further plot this graph in we can use this value to plot it into a graph as this. So as we can see, the M3 when it increases, the R square of the random forest also increases, but only until M3 equal to 8, and then it started to drop. So this double confirm that M3 equal to 8 is one of the best hyperparameter we can use to have the best accuracy, best R square. Not accuracy. Accuracy is used for classification. All right. Then we build the random forest model and check the result. We take the M3, which is the hyperparameter of random forest, to our models, M3 equal to 8, and then to see the results. And the result here, okay. So the result here saying that the variance expression is 89.85, is close to 90. So which is very, very good result compared to the linear regression. To recall, the linear only has 10, but this random forest has 89. And then we plot the error versus number of trees. So the graph is look like this. When the trees increases until, let's say, 50, and then the error drops sharply. And then starting from 50 trees, move to 500, and then it drop gradually. So which means that when the trees increases, then the error decreases. But when the trees increases, then the computing power also increase. But for our problem here, because our data set is only 5,000 observations, and then we are not very sensitive to computing power, so we use 500 trees as our parameters. Then we check the feature importance of random forest. As we can see, which means that the feature importance, which means that which feature is the most important to predict the targets, which is the total UPDRS. For age, it is 260,000, which is much larger than the second highest, DFA, sex, RPD, and so on. And so it's for our literature review for this project is actually share similar findings with previous caller, that age actually is the most important feature to predict the Parkinson's disease, which means that when age getting older, then it is more likely for someone it has Parkinson's. All right, so then we check for the training set and testing set for the R square, MAE, and RMSE. And then this is the result for the random forest. RMSE for training set is 1.46. R square for the training set is 0.98, which is very good, close to 100% already. And then MAE for training set is 1.0. RMSE for testing set 2.39. R square for testing set is 0.91. And MAE for testing set is 2.38. So from this result, we can see is it overfitting or underfitting. There is no issue for underfitting because the result is very good, 0.98, which means that the random forest is fitting all the points, learning sufficient amount, and then fitting very good and predict very good. So there's no underfitting issue. How about the overfitting? The overfitting here, there's also no issue. although the R square for testing set is slightly lower than the training set, but it's normal. Only 7% different. Normal for other data sets. It's not like has a difference of 20% or 30%. It's only different for 7%, and it's normal. So this is the residual plot. We further examine it for the residual plot. And we can see all the data points are clustered toward the center. Although it has some outliers here, but it is much better than the linear regression problem. So this is all the results here. From the linear regression, RMSE for training set is 9.8, R square is only 0.18, but our best models is random forest, which is 0.98, as mentioned just now, and R square for testing sets is 0.91 compared to the linear regression. So, all right, so what is the significance of this result? Which means that actually we can use the tele-monitoring method to predict patients, is it whether they have Parkinson's disease, without asking them to come to the clinics to have a test. For example, now Malaysia still not encouraged for movement to go outside, and then especially the pandemic is so serious. So by using this method, the patient can just stay at home, and then using the tele-monitoring method, and then they can know the result with very high accuracy. The second significance is actually from the previous literature review. Let me show you the literature review here. Actually, for the previous literature review, their best result is only until 0.8 something. Still, our team still haven't got literature that can go to 0.9 and above. So because of the random forest, then we actually can move the accuracy into 0.9 something. Yeah. So some of them using motor UPDRS as their target, which actually also indicate the severity of Parkinson's. And then some of the papers are 0.83 for the R square, 0.80, and so on. So I think it's because we done a proper way for the normalizing the removing the right skew of the attributes, then we actually can fit very well in the models and then get a good results for the R square for the training and testing sets. So I think I finished my presentation now. If you have question, you can ask.
Let me stop the stream
I
first.
think this is a very basic question. Okay.
Yeah.